So hi, welcome to PH 2021. So this is your second physics course, and this is the uh, course at MSOE where we're going to get into electricity and magnetism. And this we're going to start in chapter 21. And kind of before we get into more quantitative and mathematical concepts, let's talk about a few definitions quick. Um, and I'll also have some associated video for you that goes into more detail on these ideas. But we'll kind of cover the first few sections in this chapter as well. Uh, so when we think of electricity, I don't know about you, but I tend to think of devices. I think of phones and computers and all the stuff that we can plug into the wall. But really, this is a very mature branch of physics. So this has been largely settled since Maxwell in 1865. And we're going to get to his set of equations that really kind of concisely contain everything that we're gonna talk about this quarter. This is kind of foreshadowing in chapter 31. So that's kind of where we're headed. But these theories are compatible with relativity. They're underneath a lot of what you may have encountered in chemistry. So when you talk about, electrons in an atom, it's the electric force which is holding them in the atom. When we talk about what holds atoms together to make molecules, that's the same concepts that we're going to be talking about. So really, it's underneath so much of what makes up the world around us, even if we don't think of that maybe from the surface as being electricity and magnetism. But that is actually what's going on. To give you a kind of a point of reference, static electricity, I suspect you've encountered this before. If you've if you have like a long rug and you rub socks on it or slippers or something, and then you shock yourself on a doorknob, that's an example of the discharge of electric charge. And that's the first idea that we're going to talk about is electric charge. So electric charge, it comes in two types. There's positive and negative. So positive and negative. Positive charge, well, negative charge you probably think of first. This is generally, often, we're talking about electrons. And in terms of positive charge, that could be, positive ions, or it could be protons. As an example. So a couple important pieces of information about charges. If you have a positive charge and a negative charge, they are going to attract. So in other words, unlike charges attract, in contrast to if you have a couple positive charges or a couple of negative charges, like this, they're going to repel each other. Okay. Another kind of really important and basic idea with regards to electric charge is that you can't create or destroy charge. You can only move it around. So in Physics 2011, we talked about different kinds of conservation laws, like conservation of energy and conservation of momentum. It's a very similar idea. Charge is conserved. So, in other words, you can't create or destroy it. So when we talk about charging an object, really what you're doing is you're moving the charge. So if you have, and one way to think about this is to imagine your object is sort of in a box, or it's in like a system, a surrounding. Try and draw this halfway decently here. So if you then charge that object, just for an example, we're going to say it's positive. What that means is there must be an equivalent amount of electric negative charge in the system, so that when you add them all up, you know, if this started out neutral, no net charge, it remains neutral. So charge is conserved. What else do we want to mention about charge? You know, a good example of this, a better example than my cartoon here is an atom, right? If you make an ion out of an atom, you're not making negative charge or positive charge, I guess. You are just moving the charge. So probably the most common example is you have some negative ion because you've taken an atom and you've removed an electron from it. So, you know, maybe you have it's kind of the cartoon of this. You have some atom, you remove, you know, if this was neutral, you remove an electron from it. This combination remains neutral. Okay. What else? It's kind of the idea of charge. The next sort of important definition, pair of definitions that we have are conductors and insulators. So we talk about this in different contexts. You can, we're talking about electricity and the movement of electrical charge. So basically a conductor allows electrical charge to move, or an electrical conductor rather, allows charge to move freely and easily, whereas an insulator does not. So, you know, you can think of kind of different materials. Usually we think of this as metals, and this would be something like rubber. And, you know, kind of the go-to example to think about with this is like, well, wire is made of metal, but the insulation around the wire is made of like rubber or something else. So that's another important definition. This will become more relevant when we start talking about problems and the ability for charge to move around will be an important idea, especially with regards to like metal objects. Um, so what this part of why this is important is because it has bearing on how you charge things. So if you have a conductor, you can charge it by basically touching it because the charge can move. So suppose you have let me put a note here. So it impacts on how you can charge objects. So conductors versus insulators. And I should say I'm not going into tons of detail here because I suspect many of you know a lot of this already. And also your textbook has a lot of detail on this, so don't forget to read chapter 21. But with regards to conductors and insulators in terms of how you can charge objects, if you imagine, we'll give you a little example here. You know, if you have like some metal object, a conductor, that has a net charge and you touch it to another object that's neutral, but that is a conductor. So imagine, you know, this one's negative. What's going to happen is that charge can be transferred. So what you would end up with is the charge distributed over those two objects. Now, the total amount of charge in this picture is going to stay the same. Remember, because we can't create or destroy it, we're just moving it around. The total is conserved. You can also charge objects, kind of change this the configuration of charge in them without touching them. So I should say this is basically conduction slash touching, as opposed to the other way. The other thing that you can do is called induction. So what that would mean is, even as you get close to another object, if this is a conductor, remember opposites are going to attract. So you would accumulate positive charge on the one side of this, and like charges are going to repel, are going to try and get away. So notice the total charge on that would not have changed, but it is, we would call it polarized. The charge configuration has been changed by virtue of the fact that we've put a charged object close to it. And that's called induction. And I should mention this is talked about in around section 21.4 or so. They also describe in there a device called an electroscope, which you can use to measure the amount of charge. So, you know, if we're talking about these problems where charge has moved, etc., suppose you wanted to know how much charge an object had on it, the device that you would use to measure that is an electroscope. Okay. So those are sort of the definitions that we want to talk about. And what we're going to talk about next is the force between charges.